Let us look at question number 38 from Set 1 Civil Engineering K 2021. Refer the truss as shown in the figure. If load F is equal to 10 root 3 kilonewton, moment of inertia I is equal to 8.33 into 10 power 6 mm power 4. Area of cross section A is 10 power 4 mm squared and length L is equal to 2 meters for all the members of the truss. The compressive stress carried by the member QR is asked in kilonewton per meter squared and we are expected to report our answer in integer. Students are encouraged to watch this NPTEL lecture cited below where this topic is handled in more detail. However, we will be looking at some fundamentals as we go on to solve this problem. Let us look at some fundamentals pertaining to truss analysis. Consider the free body diagram of the truss as shown, and let us consider the truss to be in the xy plane as shown. In order to calculate the member forces in the truss, there are basically two methods that are available. The first is the method of joints, where we isolate each joint and proceed from joint to joint, thereby calculating the member forces. At each joint, since the force system is concurrent, we have only two equilibrium equations at our disposal, namely in this case sigma fx equal to 0 and sigma fy equal to 0. And this can be applied to a joint where a maximum of two unknowns are present, which pertain to the two member forces, since we have only two equations. The other method available is the method of sections. Here, we can cut intermediate sections in order to compute member forces in any intermediate member. And at each section, since the forces are not concurrent, we have three equilibrium equations at our disposal, namely sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0, taken about any point. And since three equilibrium equations are available, this method can be applied to a section with a maximum of three unknowns. However, there are some exceptions that do exist, and students are encouraged to watch the lecture cited before where these exceptions are discussed as well. With this background, let us approach the problem at hand. The first step in this analysis is to calculate the support reactions. Thus, first let us draw the free body diagram where we have replaced the hinge P with two forces, namely Vp and Hp in the vertical and horizontal direction respectively, and the roller S with a vertical restraint Vs. And let us consider this truss to be present in the xy plane. Now, applying the equilibrium equations to this free body of the truss, we can see that sigma fx equal to 0 gives us hp equal to 0, since this is the only horizontal force acting on the truss. Similarly, sigma fy equal to 0 gives vp minus f plus vs equaling 0, which gives us vp plus vs equals f. And let us take moment about the joint P, where the contribution of vs would be anti-clockwise and the contribution of f would be clockwise in nature. And from this xy coordinate system, we can see that plus z is pointing out of the plane of the paper. Hence, anti-clockwise moments would be positive and clockwise moments would be negative. Consequently, we can see that Vs into 2L is an anti-clockwise moment which is positive, minus Fl is a clockwise moment which is negative, equals 0. And from here, we can get that Vs is f by 2. Substituting this value into this equation, we can get Vp equaling f by 2. It is to be noted that we need not necessarily go by the first principles every time. By simple visual inspection of this truss, we can see that the truss is symmetrical in geometry, loading, and in member configuration. Hence, we can simply deduce that the vertical reactions are equal by symmetry and the horizontal reaction must be 0. Now that we have calculated the reactions, the next step would be to consider an appropriate section in order to calculate the member force in member QR. Now, in order to calculate member QR, it is necessary that one of the members which our section cuts must be member QR. And going by the requirement that a section should cut at most three members, we can see that we have section 1.1 or section 2.2 at our disposal in order to solve this problem. It is to be noted that irrespective of which section we consider, the final answer would come out to be the same. Let us consider section 1.1. We can see that section 1.1 has exposed FQR, FQT and FPT as shown here. Now, the general convention is to take the forces acting away from the joint, which indicates tension in the members. However, from our calculation, if we get the final answer to be negative, it would imply that our assumed direction needs to be reversed and the member is indeed in compression. Now, in order to calculate the stress in member QR, we first need to determine FQR. And in order to determine FQR, we are at liberty to apply the three equilibrium equations at a section. However, our focus here is to minimize the computational effort. Hence, we can see that FQT and FPT intersect at joint P. Hence, if we were to take the moment about point T, we can see that we can easily eliminate these two unknowns and we would get an equation purely consisting of FQR, which would lead us to the answer with the least computational effort. Now, in the question, it is given that all the members of the truss are 2 meters in length, hence PT is L, and triangle QPT is an equilateral triangle, which implies that the vertical distance from Q to T is root 3 by 2 L. Now, if we were to take the sum of moments about T equaling 0, we can see that the moment contribution of FQR would be clockwise, which is negative, and the moment contribution of Vp, which is again clockwise, negative, would add up to 0. And this gives us FQR equaling minus 2 by root 3 Vp. And from here, we can substitute Vp equal to F by 2, which gives us FQR equaling minus F by root 3, which is minus 10 root 3 by root 3, which is nothing but minus 10 kilonewton. It is to be noted that FQR has come out to be negative, which implies that the direction which we have assumed needs to be reversed and the member QR is indeed in compression. We know that truss members are subjected to axial forces. Hence, the stress in the member QR would be axial in nature, which can be given by FQR divided by area of QR, which is nothing but 2A. Hence, substituting the value of FQR to be minus 10 kilonewton and 2A as 2 into 10 power 4 converted to meter squared, we get sigma FQR as minus 500 kilonewton per meter square. Now, if the question were to ask the stress in the member QR, then we would have reported minus 500 kilonewton per meter square as our answer. However, since the question already qualifies the stress to be compressive, adding a minus sign here is redundant and hence our answer is sigma QR equal to 500 kilonewton per meter square qualified as a compressive stress. And this is our final answer. Thank you.